Our next section is 16.8, and this section is on conjugate acid-base pairs. And this was something that I defined for you at the beginning of chapter 16, but let's do a quick refresher on what conjugate acid-base pair actually is. So we're going to use this reaction HCN plus H2O in equilibrium with Cn minus and H3O plus. And so as you guys learned at the beginning of chapter 16, when we were learning how to classify whether a molecule was an acid or a base, our strategy was to take the reactant molecule, follow it through the reaction over to the right-hand side of the reaction, and ask ourselves, what did this HCN, what did it turn into? Did it turn into Cn minus, or did it turn into H3O plus? And when we're doing this, we're just looking to find the product that has the most atoms in common with the reactant. So HCN and Cn minus have these two atoms in common. That's how I'm linking them together. And then also H2O and H3O plus, that's another pair that we link together, again, because they have a lot of atoms in common. And so that was our step one, is to link each reactant up with a product. And then our step two was to determine for our two reactants whether the reactant was an acid or a base. And we were going to do that by looking at what happens to the molecule as it goes from the left side to the right side. HCN goes to Cn minus, and it does that by losing an H plus, and a molecule that loses an H plus in a reaction is an acid. So HCN is the acid. When the HCN molecule, or any acid, when it loses its H plus, the molecule that it turns into is described or labeled as the conjugate base. The acid turns into what we call a conjugate base. And then for H2O going to H3O plus, we're going to ask ourselves, how did that happen? Well, H2O gained or picked up an H plus. Anything that gains an H plus is a base, so H2O is our base. And the bases in these chemical reactions turn into products that we call conjugate acid. And together, the acid, in this case HCN, and its conjugate base, which is Cn minus, that pair is called a conjugate acid-base pair. It's a pair of molecules, one's an acid, one's a base, and they are conjugates of each other in this acid-base reaction. And likewise, H2O and H3O plus are also conjugate acid-base pairs. I'm going to abbreviate that because it's a big word. So what we want to look at is this, we have this really cool relationship between conjugate acids and bases. So we're going to say for any, I'm going to abbreviate it again, conjugate acid-base pair. For any conjugate acid-base pair, the Ka for the acid times the Kb for that base is going to be equal to Kw, 1 times 10 to the minus 14. That's a really handy relationship. There are times when we only have a Ka provided to us, but maybe we need to calculate a Kb or vice versa, and we can use this relationship to help us. Now, I want to show you where that Ka times Kb equals Kw. I want to show you where it comes from because it's actually really cool. So here is the example that we're going to use. We're just going to keep using HCN. So let's think about HCN as an acid, because that is what it is. reacting with water. All of these reactions, remember, it's always plus H2O in equilibrium. And I'm telling you that HCN is an acid, so you guys know when we're reacting an acid with water, one of the products that we make is H3O plus, and the other product is, in this case, is cyanide, CN minus. For this particular reaction, because HCN is an acid, if we were to write an equilibrium expression, we would call it a Ka because it's an acid, and it's going to be our products, H3O plus and CN minus, over our reactant, HCN. Remember that we leave out water because water is a liquid, and liquids and solids are not included in equilibrium expressions. So we got that. This is for our acid, HCN. Now, up here, right here, I said for HCN, the conjugate base of HCN is cyanide, CN minus. So let's write a reaction where cyanide is acting as a base. Always, it is our base reacting with water, so plus H2O in equilibrium. And since we are writing a reaction for a base, cyanide, one of our products is going to be hydroxide, OH minus. Bases always produce hydroxide. Acids always produce H3O plus. Our other product is going to be HCN. So we did practice predicting these products in the last section that I covered, I believe. And we can write an equilibrium expression for this as well. Because cyanide is a base, we're going to call it a Kb. And again, we're going to go products, OH minus, times HCN over the reactants, CN minus, leaving out water because it's a pure liquid. And again, all of this that we just did, the reaction and the equilibrium expression, is for our conjugate base, cyanide. So if I said, hey, let's just, take the Ka and multiply it by the Kb, and let's use our equilibrium expression. So let's take the whole entire Ka, H3O plus, CN minus, over HCN, and let's multiply all of that by the whole entire Kb. So that's going to be OH minus HCN over CN minus. You might be starting to see what's about to happen here, and you might be getting very excited. So when we multiply these together, look at what we can do. We have a cyanide on top and a cyanide on bottom. So in multiplication, they're going to cancel. And we have HCN on bottom and an HCN on top. And oh my gosh, when we multiply these together, we get H3O plus times OH minus. It simplifies down to H3O plus times OH minus. And that is the term, the definition, the equation that we use to calculate Kw. Wow. So that means that Ka times Kb for any conjugate acid-base pair is going to work out to be Kw.